I think I heard someone say once it got back to trig functions, it made you feel better.
Yes.
Something like that. So we're going from x equals 0 to x equals pi over 2. So first of all, it says cosine x. Where does cosine x start? Starts at 1, yep. And then it goes down like that, right? Because what's cosine of pi over 2? 0. So there's that. What about sine of pi over 2? What's that going to do? Where does it start? It starts at 0, and then what's it going to do? Go up. And what's going to, at pi over 2, what's sine of pi? 0. Do you agree with that? So this thing is going to go up, down, and then up again because it's been compressed this way, right? Does everybody understand that? So what's this thing going to do? It's going to go up, down, and up. Is that true? Is that true? Is it? I'm just asking. Is it true? Yeah, it seems like it's true. Now, my graph a little bit. I think it's okay. So we're supposed to solve sine of 2x is equal to what? Cosine x. Now, here's the thing. Can you solve that by hand? What? What? Not easily. What would you need to know? What would you need to remember if you were going to solve that by hand? Yes, how to expand sine of 2x. Very good. Yeah. Do you generally know that stuff here? You might. We could try. But at this point, if this was something you had this for, what should you really just use right now? Calculator. Absolutely. So there's sine 2x, right? And then what do we have right here? Cosine x. So how many regions are there? Well, let's zoom in a little bit here. Let's zoom box. We're going from 0 to 2 pi, right? So let's go a little bit less than that. Let's go a little bit higher than 1, and let's go over. We're going to pi over 2, right? Pi over 2 is approximately, yeah, exactly. So this is this. So was my graph accurate? Not really. Mainly because I didn't really get the curvature of cosine correct. So that's what it actually looks like. So how many regions are there actually? 2. So my rough sketch was not super good. My rough sketch was not super good. So this right here is not accurate. So if we're going to do this, what do we need to find? We know where 2 of the intersection points are. Where are 2 of the intersection points? 0 and pi over 2, right? So we have intersection at 0 and we have intersection at pi over 2. So what do we need to find now? Where they intersect in the middle, and does it look like it's pi over 4? No, it's not. So you're going to back to this, and what do you use? Second calc, right? Intersect, and you do first curve, second curve, and then you give it a guess, because when it's doing this, it's not solving this algebraically. It's estimating using Newton's method, which you've studied before. So hey, there it is. The intersection is right there. So here's the thing. You see that decimal point? Many of you might write down that decimal point. Your calculator has just saved that value as x. But you use x all the time, so what should you do at this point? Like literally, if you went in and pressed x, press enter, there's that decimal. One thing that is very helpful is you take x and you hit store and then you save it as something else. Why is it very useful to do that? It keeps it accurate, but why? Why does it help to save it as something else? Why don't we just keep it as x? If you change something, x tends to get overwritten all the time. You run another calculation, find a different intersection, it'll get overwritten. So now, though, we have that stored as A. How many regions do we have? We'll call this one R1, and there's an R, so how many regions? 2 of them, right? The key thing, though, is this is cosine x, right? And this is sine 2x. So what's the first integral for R1? What does R1 equal? The integral from 0 to A of cosine x minus sine 2x dx. And what does R2 is equal to? A to 0 of sine 2x minus cosine x dx. Oh, a to pi over 2. Sorry, not 0. Pi over 2, exactly. Now, on your if you have your calculator, you definitely use it. The way you would do that, where's integration? Math, which one is it? I think it's 9, right? And you're integrating from, if you have an 84 or above, I can update it so it'll look like this. Let's do the first one. It goes from 0 to what? You literally can write in A right here. And what was our upper function? Cosine, right? You can just do what, but y1 was, we put it, yeah, y2, exactly, right. So let's do that here. It was y2. Is it pi over 6? It is. Ah, okay. So, nice. Okay. But we didn't solve it like that. We didn't do the algebra. We need to use the double angle for it. But when you get a nice answer like that, when it comes out to something like pi over 6, what does that suggest about the algebra you theoretically could do to solve it? It could be all right. But we didn't know that until we did it with the calculator. And do we already have a number that is accurate enough? Yes, we do. So it goes from, it's y2 minus, oh, not y we want to do, sorry, y1, right? And it's dx. We hit enter. Hey, look at that. And when you get a nice answer like that, what does it tell you? Hey, everything theoretically could be all right. Okay, so that's the first one. That was the area of R1 right here. So what do we do for R2? Second entry, but what do we... Oh, second quit, sorry. What do we do for our entry here? What do we change? Yeah, so it's going to be... This goes to what? Second pi divided by 2, right? And it starts at what? A. And we change it to y1 minus y2. And we hit enter. Is it actually the same? Is that possible? Yeah, it's certainly possible. I mean, let's just look at it visually just to see if that actually makes sense. Let's just see if that makes sense here. The other one's longer, but it seems a little skinnier. So could that be the case? Yeah. If you got one was significantly bigger than the other, would that be a problem? Yes, absolutely. Now, if you did this by hand, you could, but generally speaking, you don't remember your sine of 2 theta. I mean, I even forget it off the top of my head most days. If we wanted to type this into our calculator, what would we need to solve for? Y. We would have to solve for y, and it would allow us to break it into how many functions? So y we know is equal to plus or minus the square root of x squared times x plus 3. So you could simplify that. You could say that's equal to plus or minus x times the square root of x plus 3. Now, if you wanted to graph this, you could type in each function separately and see what it looks like. Let's do that right. And then the negative 1 right here is y equals negative x to the square root of x plus 3. Okay, so if we're finding this region right here, we have our upper function and our lower function, right? So we have the integral of our upper function, which is going to be negative x times the square root of x plus 3. And what are we going to subtract from it? X plus 3, correct? And it's dx. Now, what's the trick here? What haven't we figured? What haven't we added in yet? The limits of integration. Which one do we know certainly? Which one's the easy one to find? 0. And it's going to 0, right? Correct. And what's it starting at? It's pretty easy to see. Where does that thing cross the x-axis? Negative 3. Now, here's the thing. Can you simplify this a little bit? Does this simplify? Yeah, it turns into negative 2 times the integral from negative 3 to 0 of x root x plus 3 dx. Is that correct? You get negative 2 of them. You can flip the order of integration if you want. It doesn't really matter. But the key thing is, can you integrate this by hand? Can you integrate this by hand? What would you try? You have maybe use substitution. That's like the only thing left. Does use substitution work? No. The degree on the inside is 1. The degree on the outside is 1. If you do a use substitution with x plus 3, does it cancel on the outside? No. So what are you going to have to use? You must use your calculator. You must use your calculator. You see a little icon next to the problem right here? Right here? That means you're going to have to use your calculator, as far as I understand it. So x squared is equal to c squared, so x is equal to plus or minus c. So we're integrating from negative c to positive c. Can we simplify this thing? It's going to be the integral negative c to positive c of what? 2c squared minus 2x squared, and it's dx. What can we factor out? So we have 2 times the integral negative c to c of c squared minus dx. Now you're integrating with respect to what? X. You're integrating with respect to x. What is the integral of c squared with respect to x? Nope, c is a constant. No, we're not integrating. We're integrating not c squared x. Thank you. So it's 2 times c squared x minus what? What's the integral of x squared? 1/3 x cubed, and we're going from negative c to c. So you have 2 times c cubed minus 1/3 c cubed minus negative c cubed plus 1/3 c cubed. Do you see where what's the easiest way to make a mistake on this? The negative signs, right? First we take c and we plug it in and we get these two right there. Is that correct? I think so. And then we plug in negative c, so the signs flip. So what are you left with? 2 times what? You end up with not 4/3. How many c squareds there? C cubed, 2/3 c cubed, right? And then you're subtracting, what are you subtracting? Negative 2/3 c cubed. Is that correct? So you end up with 8/3 c cubed. Is that correct? Does that look correct? It helps. There's 10 of you, there's 1 of me. That's correct. So here's the thing. What do we want that to be equal to? 576, so we make that equal to 576. So c cubed is equal to 576 times 3/8. Anybody have that? What is 576 times 3/8? Anybody have it? When you get answers like that, is that a good thing? Yes. If I randomly picked 2 functions and I randomly picked an area for their intersection, what's the chance that it randomly comes out to a nice integer value? Not very good. So when you get an answer like that's a good thing. Or it means you've fallen into some trap they've designed. Just be careful. Just be careful. How do we feel about this stuff? Let S be a solid that lies between x equals a and x equals b. So we're just looking at some solid. We've been looking at we've been looking at areas that are defined by like 2 functions. They'd be the 2 intersection points. If the cross-sectional area S in the plane PX through x and perpendicular to the x-axis. So we're slicing this perpendicular to the x-axis. So you have a shape, and you're just slicing it up perpendicular to the x-axis. Where a is a continuous function, then the volume of S is this thing right here. And what the heck does this say? Well, when you have this limit up here, what are you really doing here? What does the sigma mean? What does sigma mean right here? The sum, right? And how many things? Nope. A lot, okay? Be more specific. How many things? Infinite. No, because n is going to infinity. So it's an infinite number of things. So we're adding together an infinite number of things. And what are those things? This represents thickness, so change in x. So this is the thickness of a slice. And this is going to be the area of one slice. If I have... Let's say I had a tube like this, like a dowel, and I sliced it right here. So I just have this bottom slice right here. Everybody see that bottom slice? This is the height right here. So the height is this little tiny piece right here. A of x is going to be the surface area right here. This is going to be the surface area, A of x right there. This right here correlates to delta x. If you multiply A of x by delta x, what do you get? The volume of that slice. So what do you see up here? You see delta x right here times A of xi. It's okay if you don't understand that specific A star and the sub I right now, but the point is, if you multiply surface area by a thickness, what do you get? A volume, exactly. So let's look at the first thing you probably integrated that was more than just a line. So let's say we had this function right here, y equals x squared. Have you integrated things like that before? Yeah. So let's go from, I don't know, let's go from 2 all the way to 4. This is not 100% to scale, but it's to scale. Okay. So when we want to find the area of that, what did we do? We do the integral from 2 to 4 of what? X squared dx, right? What we're essentially doing right there is we're essentially adding up a bunch of 2-dimensional just slices, right? We have little tiny boxes, right? What's the height of each of these? What's the height of them? Y, f of x, which is also called in this case x squared. All 3 different ways to say the same thing, right? So the height is x squared. What's the width of each of these pieces? Dx. It's right there. This right here is the width of each of these slices, right? So we have width, we have height. Now, if we wanted to make this a volume, all we need to add in is a 3rd dimension, right? We need to add a 3rd thing. So one of the simplest things we could do, for example, let's define a non-rotational solid. I'm going to tell you this. You have something that's sitting on the table in front of you, and this is the footprint right here. This is what the footprint looks like. Let me just go all the way up to here and all the way down. So it's sitting on the table in front of you, and that's the footprint. Can everybody see it in front of them? It's right there on the table in front of you. Yeah. Got it? There's an x-axis and a y-axis. You're looking down, you're seeing it. Can you pretty easily find the area of the footprint? Okay, now you have a shape. Now that's the footprint of an object, okay? I'm telling you, we're going to take a big knife and we're going to slice it perpendicular to the x-axis. So we're going to make lots of slices like this, but they're going to be perfectly perpendicular to the x-axis. Everybody okay with that? We're going to look this way. We're going to look from the side. We're going to slice it and look from the side. What's a simple shape? What's the simplest shape you can think of? Let's say a square. Let's say a square, okay? Square, it's nice. It's easy to find the area. You need one side and you multiply it by itself, right? So what I'm telling you is this shape. This is the footprint, and we're going to slice it. And what you're going to see if you look from the side, from that arrow, is you're going to see squares. Every time you slice it, you're going to see a square. You're going to slice it, you're going to see a square. You're going to slice it, you're going to see a square. You're going to slice it, you're going to see a square. We have just created a three-dimensional object. What does this thing look like? It's a little hard to see, but the point is if you stacked up a bunch of squares on their side, you would see this thing. The question I'm going to ask is, what is the volume of that shape if each cross-section is a square? And this is actually really easy to find out, because is it really easy to find the area of one square? Sure, it is. Absolutely. So think about it this way. So basically what's going on is there is a square, and these are, I'm bending these a little bit so you can see them. You see these squares that are coming up here? They get bigger. The squares get bigger as you go to the right because the height gets bigger. Do you agree with that? So right here, you have 2, goes up 2, goes down 2. So you add them all together. Those are all squares. Are we okay with that? If this right here is x, what's the height of that? What's the height? The height is, we already established the height is what? X squared. What is the area of a square that has a side length of x squared? X to the 4th. If one side is x squared, how do you find the area? You multiply x squared by x squared, right? So actually the volume of this thing, you're still going from 2 to 4. What is the surface area of any slice? X squared squared. What's the width of any piece? It's still what? No, of each piece, dx. This right here represents the volume right there, because all we've done is we've added in a next dimension. This case, it was a square. That's pretty easy to do. Another shape that's pretty easy that you see when you see cross sections, you see semicircles. That's half a circle, right? So instead, what does this thing look like? Well, you have, let's say you went from 2 to 4 again, so we're going from 2 to 4. But instead of squares, we're going to have semicircles popping up. Oh, that's a really poor one. So do you see what kind of shape I'm drawing here? So the biggest one goes like this. So do you see what the shape looks like if I had it in front of me? It's like a half cornucopia kind of thing. It's getting bigger. Do you agree with that? You see what I'm saying? So let's say I looked at one slice. I'm looking at this slice right here. And again, this is y equals x squared. If I looked at one slice right here, you need to come up with, if this is x, what's the area of one slice if that's x? That's half of a circle, correct? What's the diameter of that circle? The diameter is, yes. So what's the radius? So what's the area of a slice? What's the area of a slice? Pi x squared over 2 squared all over 2. Why is it all over 2? It's half, right? That is the area of one slice. This is the A of x. This is the area of one slice. What's the width of each slice? Dx. So we're integrating from 2 to 4 of, let's pull some stuff. We can do pi times x squared over 2 squared all over 2 times what? Dx. That's it. That's all it is. When the cross sections are functions that you know, it's really straightforward. The most common cross sections you will see are squares, semicircles, and then the one that they're kind of gonna like slap you a little bit with is equilateral triangle. And why is equilateral triangle a little bit annoying? Because do you remember the area of an equilateral triangle in terms of a side length off the top of your head? S squared root 3 over 4. Do you remember that? It kind of rings a bell in your head. Remember the height of an equilateral? You need base times height, right? So you need the height of an equilateral triangle. But does it really matter? No, you can determine that on your own. You should be able to. The point is, the only difference between area and volume is you just need another dimension. So the first thing we're going to do is cross sections that have known areas. Cross sections with really easy